this work is, all of it is done with my very dear friend and colleague, Professor Amitabh Sanyal. And ideally, he should have been giving the talk here because whatever I've learned about this area is from him. But he could not come. I mean, he's the one who helped me a lot with the slides and all of that. So while I'm presenting, I think it should really have been Professor Sanyal here. Okay, I'm going to talk about this topic called translation validation. My background is in formal verification, and this is where I think the compiler's technology meets formal verification. We want to have trusted compilation. So of course, to this audience, I don't need to say that compilers are everywhere. I just picked up some numbers yesterday from the internet that an excess of 250 million PCs are sold every year, and each of these PCs, or at least most of them, come either with Windows, Mac, or Linux, or I guess these days there are some other OS also, but most of the market is really this. And each such OS actually ships with a compiler. There is a compiler that's already on your PC if it's running, if it has come with one of these. And so the question is that, the title of my talk was towards trusted compilation, but after all the sessions here and all the beautiful talks that I heard today, I would like to ask you that, have you ever not trusted a compiler? Did this thought even cross your mind that, okay, yes, okay. So what was the evidence? I mean, nothing? Oh, okay. It just crossed your mind that, yeah, so I mean, we often take compilers for granted, I mean, it's like something that's of course there, it's, shipped with every major operating system that's out there. We use it routinely, otherwise how would we even do our software development, how would we build systems and all of that if we did not have compilers and if we could not trust the compilers. So as programmers, as compiler developers yourself, and the large majority of analysis tools, we often reason at the source code level. We look at source code, maybe at different levels of abstraction, intermediate language, we heard some talks about that. And of course there are tools and techniques to reason about the machine code also, but the largest majority of analysis that we do is often at a higher level of abstraction, and something translates from there down to the machine code, and that's the compiler. So the implicit assumption is that a correct source program compiles to correct machine code. Okay, so we put a lot of effort. I mean, just this over lunch, we were having some discussion with some colleagues about what is the code that goes inside an electronic voting machine, and could we verify it and all of that. But the implicit assumption that we have is that if I can look at the source code, in some form, Java, Rust, C, C++, whatever, and if I could do some analysis and convince myself that, yeah, this code is doing the right thing, after that, the compiler is of course doing the right thing, and so if my source code is correct, the machine code will also be correct. But, this is an assumption at the end of the day, unless somebody really gives us a proof that this is indeed the case. This is an assumption. And why is it an assumption? Because compilers are, I don't need to, convince this audience, they are extremely complex and sophisticated pieces of software, and there is no reason why bugs could not be lurking in there. I mean, with software at this complexity level, there could very well be bugs. I mean, most likely there are bugs there. And so what if this assumption wasn't true, and just think of, applications like maybe it's a, radiation machine which is administering radiation therapy to a cancer patient, and some software is running there which has been compiled down to some machine code. There are some, microprocessors in that machine, and if the compiler makes a mistake, and because of that, if the machine ends up delivering lethal doses of radiation, that can cause loss of human lives. Okay, railway signaling. I mean, I don't need to tell this audience what happens when railway signaling goes berserk. Controllers of nuclear reactors, fly-by-wire systems. So anything on which there is code running, and a problem with that code can have disastrous consequences. This code, in all probability, was not written in machine code, although what is running is machine code. Somebody wrote some code in a higher level language, used a compiler to get it down to the machine code, which is running there. And what if that compiler had a bug? Okay. And you know, so one might say, yeah, of course, you know, this looks like you know, doomsday predictions, but you know, we've all worked with compilers, and how frequently did we see? I mean, I just saw one hand going up when I said, how many of you don't trust a compiler? So are we really raking up a non-issue? I mean, yes, it could happen, but maybe the probability of it is habits like, you know, what is the probability that this roof will fall on our heads? There is a non-zero probability, but should we really bother about it? Right? So the question is, have you actually witnessed a buggy compilation by, let us say, a production compiler, GCC or LLVM? Yes, it can happen, maybe in some corner case, but have you ever witnessed anything? And you know, typically the argument is that, well, these are open source pieces of software. There's such a large community. You know, everybody in this room have probably looked at the compiler code at some time, some compilers code at some time. There's extensive scrutiny being used for decades. How can there be a bug? So we often try to equate this with that there are no bugs. Okay. So you thought that compilers were really bug-free in practice, and this is a few days back from the GCC Bugzilla list, which is every day it gets populated with issues, some of which are, I'll show what kind of issues they are, but some of them are actually real bugs. Okay, and this list gets updated, so you can, you know, if you can see, you can go to that website right now as we are speaking, and you will see that, you know, more things have been added since I took the screenshot from there. So it is not a non-issue. I mean, this is actually out there. It may not have affected you today, it may not have affected anybody you know today, but that is no guarantee that there is no bug, and that is no guarantee that it's not going to affect you the next day. Okay? So this is a real problem, and we need to do something to sort of address this problem, right? I mean, we can't say we'll start coding in machine language. We don't trust compilers. That's not a solution. We have to use higher level languages. We have to use compilers that translate them to machine language, but these compilers are so complex and sophisticated that there's likely to be bugs there. So, you know, the kind of thing that is reported over here, not all of this is kind of very dangerous or very, you know, catastrophic in its consequence. So, you know, we've just tried to categorize these as in three groups. So these are the internal compiler errors. The compiler crashes during compilation, and I've given some identifier of a actual bug report there in this GCC Bugzilla. So, so here one might say that, well, if I was trying to compile the code and the compiler crashed, I know that there is a bug. Okay, so I'm not going to run the wrong machine code wherever I was trying to run. There could be missed optimization opportunities. You know, the program is correct, functionally correct, but it did not optimize something that it could have optimized, so it could be a suboptimal performance. These are also categorized as bugs in that list. But I will ignore these things because these are things that, you know, don't have catastrophic consequences. In the first case, I know the compiler had a problem. In the second case, it's functionally correct. Maybe performance-wise, it was not good enough. The third one is the more serious one, where the compiler doesn't crash. It comes out saying successfully compiled. It says it has done a lot of optimizations. Whether it has missed optimization opportunities or not is irrelevant. But in the process, it has actually changed the meaning of the program. So it has not done a correct optimization. Okay? So the source and the target programs exhibit different behaviors, and once again, that's a reference to an actual bug report in the Bugzilla, where, and this is serious, right? Because there's absolutely no indication. Silently, you go ahead, the compiler goes ahead with its job, and you pick up the code, trust the compiler, and you try to run it on something, and there is a problem. Okay? What you get is not what you started off with. The source and the target don't have the same observable behaviors. So this is absolutely unacceptable, and this is going to be the focus of my talk today. And the specific compiler, I have written GCC because that's the one that, you know, Professor Sanyal and I have been working with. But the talk today will be at a slightly higher level, so this should apply to any other compiler that you are more familiar with. But the work that we have been doing specifically applies to GCC. Okay, so this last category of bugs, which are the ones that the compiler silently goes ahead and there's no way for you to know that the meaning of the program has changed. So just to illustrate that how subtle these bugs can be, I don't know if the code is visible from there. Can those at the end you can see? Okay, great. So this is a one-line program, function bar, two versions of it, takes an unsigned integer, and in the first case it compares -1 with a bit masking of x, and in the second case it compares x with a bit masking of x. And the question is, what should bar -1 return, right? If you look at the value of x, it's -1, so it would almost appear that they would return the same thing. You know, I'm not projecting from my laptop, so in my laptop I wanted to show you, compile it and see what it does. So what do you think? I mean, any guesses of what the left program in a right compilation? So this is C language, in the C semantics would give me. And would it differ from what the compilation from the, I mean, of course, the reason I've put up these two programs is because they must differ. Why would I put it up otherwise over here? But and the answer is either true or false. This is a Boolean comparison. So which one is true and which one is false? Yes? Left is? Okay, so in the left what is happening is there is a negative number, negative constant, which is being compared with something. No, but -1 is a negative integer. So this becomes this becomes a signed comparison. Whereas over here this becomes an unsigned comparison. And when you mask -1, the argument is -1, so it's basically being represented by all ones. And when you mask it with 1, you're going to get 1. So in one case you are asking signed comparison -1 less than or equal to 1. That's false. But in the other case, it is an unsigned all ones less than or equal to 1. Sorry, in the first case it is true because -1 is indeed less than or equal to 1. And in this case, it's an unsigned all ones less than or equal to 1. That's false. So it turns out that this is actually not something I created. This was an actual bug in one of the most trusted compilers that we have today. I'm going to talk a little bit about it, which is called CompCert. And CompCert produced a 0 for that over there. Code, I mean the compiled code after CompCert was used produced a 0. Of course, this was in the buggy version. It has now been fixed. Whereas, GCC would actually produce a 1, right? Because there's a signed comparison and there's an unsigned comparison. So when you're talking about correctness of a compiler, the semantics of the language comes in, what the language reference manual says, undefined behaviors come in, all of these come in. I mean, before you declare that a compiler has done something that it was not allowed to do, you have to make sure that it is against what the semantics allows, right? And if you look at for example, the C11 semantics, a lot of things are left unspecified, right? For example, if you're doing a division by 0, what exactly should happen is left unspecified. So different compilers can differ on that, but all of those are correct behavior. But in this case, the language reference manual says that that should be treated as a signed comparison and this is an unsigned comparison, and therefore here it was definitely an error. Okay, so compiler bugs can be subtle. It's not always that you need a very large complex piece of code to have a buggy compilation. So this is going to be tricky. Okay. Now this one that I showed was this bug crept in because of an incorrect interpretation of the less than or equal to operator, whether it was a signed or an unsigned. Bugs can also creep in because of incorrect optimizations. So once again, I'm showing two programs. Let's focus on the program on the left to begin with. So there are two integer there is a single element array, G. There are two integer pointers, P and Q, which are both pointing to that first element of the array, the only element in the array. And then there is a function foo, which is assigning G0 to 1. Then it says star P is 0 and star P is star Q. And then it says return 0. So what should it return? What should it return? It should return 0, right? Because star P is pointing, right? P is pointing to G0 and all of that should finally return a 0. But it turns out that in an earlier version of GCC, I mean this actually comes from the Bugzilla reports, that star P is 0 followed by star P is star Q almost looks like something was overwritten. There was an assignment and immediately it was overwritten. So that star P is 0 got removed in an actually earlier version of GCC. This is in the Bugzilla reports. And if you compile away, if you optimize away that star P is 0, you will get the answer as 1, which is wrong, right? So this was an optimization that the compiler was trying to make the code faster, saying that you're making two assignments immediately, one after the other, to the same address, so I should just keep the second one, but then, that's incorrect. It's not allowed to do that. So if you do the optimization incorrectly, the answer can be wrong. The one on the right is actually, if you look at this code, there is a loop which goes from 0 to 5, 0 to 4. And of course, when x is 0, it will not satisfy both of the if conditions. So it will go back and then start at x is 1. And for 1, 2, 3, 4, the first continue itself will take it back. So it will never come to the break. So it should actually come out with the answer 5, right? If I'm trying to return x, it should come out as 5, right? Everybody agrees? It turns out that an older buggy version of LLVM applied this scalar evolution pass, and as a result, it incorrectly predicted the value of x. So the buggy scalar evolution pass figured out that, well, this code is not really doing anything, and so it sort of said that, in this particular case, it said that the value of so it basically replaced this entire code with x equal to 1. Okay, it did the scalar evolution and said that the code can go away. So once again, some optimizations that were not correct happened, and because of that, the meaning of the program changed. Okay, so now that I believe all of us agree that yes, there can be compiler bugs and we need to be worried about them, particularly if they're changing the meaning of the program. So the question is, how do we hunt down these bugs? Because we have to figure them out, right? I mean, you take your favorite compiler and then, the question before you is, does this compiler have bugs? So the traditional software testing approaches are not very effective for this, because think about a compiler. What is the input of a compiler? It's a program. And how complex can programs get? Arbitrarily complex. Right? Unless you're talking about a very toy language which allows you just one assignment statement. Any real programming language, the input to the compiler, right? A test generator generates an input to the program that you're trying to test, right? It could be, in normal cases, it could be an array of integers, it could be some values of scalars, this, that. But for a compiler, it has to generate a program. And the output is the target program, and somehow you have to figure out that this is not what the compiler should have output. Because testing, the entire process of testing is this, right? You give an input and you have an expected output, and you check whether that expected output matches the actual output. If not, you say that the test has got a bug. If yes, you say that the test has passed. But here our inputs are programs which could be arbitrarily complex. The outputs are also programs which could be arbitrarily complex. And we have to somehow figure out, somebody has to tell us that yes, for this source program, that was a correct target program, and that was not an incorrect target program. So this is not going to be, so this is kind of, although in principle, in theory, yes, a compiler is also a piece of software, so we should be able to apply software testing techniques, but that doesn't really work over here. Okay, so a pragmatic approach was actually proposed in, actually a very nice approach in this tool called CSmith, which appeared in a PLDI 2011 paper. It's a very interesting technique which says generate some quote-unquote random C programs. The paper talks about what kind of programs. So these are actually small programs, they're not large programs, but which try to exercise some corner cases which compilers are likely to have forgotten to take care of. Kind of thing that I showed, that you have an unsigned comparison, but in one case you have an unsigned constant, in the other case you have in one case you have a signed constant, in the other case you have an unsigned variable. So it's not completely random, but some kind of guided random C programs. And then you compile it with multiple production compilers. So you see that you're not just testing one thing. It's not just I give you GCC and you're trying to come up with test cases for GCC. And then, if these executables, once again, you run them on some test cases which are also generated in some, guided manner. And if the executables produce different outputs, then you know that at least one of them is wrong. Not all of them can be correct, right? And whichever one, the minority group, so if you keep an odd number of compilers here, you will know that at least there is a minority group that must be incorrect. I mean, at least one of them must be incorrect, and you go and scrutinize the minority group. And in fact, this paper was very influential. It actually discovered at that time 325 bugs, as reported in the paper, in widely used compilers. And these bugs were not known to the compiler community, to none of these communities at that point. So it had a major impact. There were numerous bug fixes, modifications in compilation strategies, and all of that. And so this is, one kind of technique that people still try to use when they're trying to hunt down compilation bugs. But note that this method can show you the presence of a bug, but it cannot show you the absence of a bug. Because at the end, I mean, that's true for all of testing, right? Testing can show you the presence of a bug, but not the absence of a bug. So this is an effective testing technique for compilers, but it can't show you the absence of a bug. Okay? So how do we show the absence of compilation bugs? I mean, that's what trusted compilation would mean, that here is a guarantee that the compilation was correct. So a very, very high level view of bug freeness in a compiler. I've tried to write it down here. Don't treat it as a very mathematically rigorous statement. This is just trying to express the intuition. So when would I call a compiler bug free? That for every syntactically correct source program that I can give to it, and for every input that program accepts, the behavior of the source program on that input should be, that's the wiggly equality, should somehow be the same, and we'll define precisely what that means, somehow be the same, to the behavior of what the compiled version of the source program is on the same input. Right? So we are saying that my compiler, the part in red, is bug free if for every legitimate source program I can feed to it, and for every input I can feed to that source program, whatever the behavior of the source program would have been on that input would be the same as the behavior of the compiled version of the source program on the input. If my compiler can guarantee this, then it is bug free. Okay? But of course, it's easy to write it down. It's almost impossible to get this achieved in practice. But then, in this community that has been looking at correctness of compilers, there have been two approaches to try to achieve this very high level goal. One is called certified compilation, where the source program is assumed to be symbolic. I could have infinitely many source programs, so I can't just give one source program after the other, right? You take C language, there are infinitely many source programs, legitimate, syntactically correct source programs. So you take the source program to be symbolic, you take the program input to be symbolic, and then you try to ask whether the behavior of the source program, the symbolic source program on the symbolic input, is the same as whatever the compiler would do on this symbolic source program. So it would give you a symbolic target program, and right, what would that symbolic? So I mean, this is at a very high level I'm talking about. So this requires reasoning in, as you can imagine, higher order logic, right? Because we have to talk about programs which themselves transform states, and then the compiler which is transforming the program and all of that. But if I could do this, then I could guarantee the correctness of all runs of that red compiler. right? Because that's what it is saying at a high level. And indeed, Xavier Leroy in Popple 2006, I mean, this was considered an absolute landmark, and I think he has won several awards for this. He actually developed a compiler called ComCert, which took not the whole of C, but a fairly large fragment of C. A lot of programs that people would write can be written in this. And he actually showed a proof for whatever I've written above over here in a very hand wavy term. He actually gave a proof of this in higher order logic using a proof assistant like Coq, and this was considered an absolute major landmark. Unfortunately, since then we have not had another similar successful effort, which sort of testifies to the difficulty of this endeavor. I mean, it's okay to write it down, I can write it down in a line, but it takes years, decades to actually get this done. The other approach is what I'm going to talk about, because, I'm not as brave at heart to try a certified compiler, is to say that, okay, let's make the source program concrete. So I'm not going to be reasoning about all source programs, but you give me your source program. But I will reason about all possible inputs to that source program. Okay? So it's the same setting, but now I'm talking about a specific source program, all possible inputs, so the inputs are still symbolic. And I will say that this specific source program on whatever symbolic input, however it behaves, and the compiler working on the specific source program will give me a specific target program. How does that program behave on the symbolic input? Okay? So as you can see, this is a much simpler problem, right? I'm talking about a specific concrete source program. And it turns out, as we will see, that logics for program verification are almost sufficient. We have to do a little bit more. For example, we can do Hoare logic with first order or separation logic predicates, and this almost suffices for this. Okay? But then this means that, remember that comp was my compiler and I was trying to certify its correctness. And if I can show this for my concrete program, all it means that that concrete program got compiled correctly. The next concrete program may not pass this test, right? So whereas in the previous case, there was a guarantee of correctness of all compiler runs, but here when I'm fixing a concrete source program and doing the proof, I only get to know that that particular source program was compiled correctly. The next source program may or may not be compiled correctly. So it's not a guarantee on the correctness of the compiler, it's a guarantee on the correctness of a specific run of the compiler on a given source program, right? So that's the difference between certified compilation and translation validation. So translation validation is inherently a much simpler problem, at least if you look at it this way, than certified compilation, right? So I hope this difference is clear to everybody. All right. So now I talked about this, wiggly equal over there, saying that, source program running on some input and the compiled version of the source program running on the same input, they should behave similarly. So what does it mean? It means that I'm not going to look at the internals of the program. I'm going to look at the program as a black box, both P1 and P2 as black boxes. And these are black boxes that will consume values given by the user through statements, or need not even be from the user. They could be from whatever, other library modules, or from the OS or whatever. Basically, the program consumes values through input statements, and the program produces values through output statements. And I'm going to view a program as a black box that consumes some values and produces some values. So it could consume a sequence of values. The inputs could be in a loop. In a loop, I'm reading inputs. I could be outputting in a loop, and so on. And we will say that these two programs are having the similar behavior if what we can observe is the same, which means that they're executing the same sequence of inputs. They're asking for the same kinds and numbers of inputs. And if I provide them the same inputs, but I'm allowed to provide arbitrary inputs, but if I provide an input 1 to the first one, to the first request of P1, if I provide 1, to the first request of P2, I'll also have to provide 1. To the second request of P1 input request, if I provide 5, to the second input request of P2, also have to provide 5. So assuming each corresponding input statement pair reads the same value, but this value could be anything arbitrary, they will produce the same sequence of outputs. So this is what we mean at a very high level. Of course, once again, this is not exactly rigorous as a mathematical statement, but I thought, putting this way will at least help convey the intuition. This is what we mean that the two programs are behaving identically. If they take the same inputs, they give the same outputs. So there's no way to distinguish between them if I view them as a black box. Okay, so our ask from a translation validator would therefore be that I give you a source program which could be in a particular language, let's say L, and the source program is now compiled to a target program in a language L prime. We have to either show that PL and PL prime have identical observable behaviors, or we have to demonstrate distinct observable behaviors. Right? Observably distinct behaviors we have to demonstrate. So either we have to establish that PL and PL prime have identical behaviors. Whenever I give them the same sequences of inputs, they produce the same sequences of outputs, or I have to come up with one sequence of inputs for which they produce different sequence of outputs. So, which means that I have to come up with a concrete input sequence for which the output sequence of PL and PL prime differ. Okay? And this is what Professor Sanyal and I have been trying to do. The compiler in our case is GCC, but as I said, what I'm talking about is not restricted to GCC. Our input is a C program. The output is a program in the machine code of x86, 64 bits. And we would like, our goal, the ideal holy grail would be to come up with a box over there, the translation validator, which either says, yes, they have provably the same behavior, and also gives me a proof of that, or they say, it says incorrect, and it demonstrates the different behavior. This is the holy grail. This is what we'd like to do. It is not. I'm coming to that. I'm coming to that. Yeah. So, but there's one additional point I would like to sort of bring up over here, that this translation validation business doesn't have to be, with the C and the assembly code. Most modern optimizing compilers will have many optimization passes, and maybe one of those optimization passes is buggy, and I could therefore do this taking the inputs and outputs of each optimization pass. And actually all of these compilers, if you instrument them, if you give the right option, they will keep dumping whatever the intermediate form is, and then you can take these two intermediate forms at the input and output of a pass, and you could do an validation of an optimizing pass, and you could figure out maybe the version of GCC I'm running has everything correct, but maybe it's whatever conditional constant propagation has a bug, but everything else is correct. But then maybe I can disable that pass and everything would be okay. Okay. So that is what, so our work's focus has also been at this level, and if I can of course show that all of the passes are correct, then the end-to-end thing is correct. So yes, as you said, that are we really asking for the moon? Yes, and it's not very difficult to show that this is not a decidable problem, which means that it is impossible. It's not that just we are not smart enough, but it's a mathematical impossibility to algorithmically determine if every translation is correct or incorrect. Okay. So therefore, we will have a reduced ask, which is to ask for a sound approximation. Now that we know that the exact problem cannot be solved algorithmically, we'll try the best possible that we can. So we'll say, okay, we will try to identify as many correct or incorrect translations as possible, but things that, because of this undecidability, we won't be able to do this for everything. So the rest we will mark as possibly incorrect or unknown. Why is it possibly incorrect? Why not possibly correct? Because unless I'm able to get a proof that it is correct, I cannot say that it is correct. So maybe there is some part of it that I have not been able to check properly. But we never want to give a wrong answer. If we say it is correct, there should be a proof that it is correct. If we say it is incorrect, we should have a demonstration that it is incorrect. And of course, if we say I don't know, then right. So one easy way out of it is to say, always say I don't know. That's also a sound approximation, but that's not a very useful sound approximation. So we would like to minimize that middle part as much as possible and maximize the first part. Okay. So I've hopefully now conveyed to you what we mean by translation validation. And we are trying to talk about how a program behaves over some inputs, but not just how one program, but the source and the target, how their behaviors compare. So it will be useful to sort of see how does program verification, how does it compare with translation validation, in the sense that what is different, what is same between the two. I mean, clearly there are properties of programs we're talking about. So the differences are that unlike sequential program verification, translation validation has to reason simultaneously about two programs, right? The program that went inside the compiler and the program that came out of the compiler. So does it look like reasoning about two concurrent programs running? But unlike concurrent program verification also, so in concurrent programs what happens is there are two programs running, but then they may have a shared memory. So they might go and access and change the same memory location. But in translation validation, the memory spaces are completely distinct, right? Because we are talking about the program before it went into the compiler pass and the program after it went into the compiler pass. The program before the compiler pass never interferes with the program after the compiler pass. So they're working on disjoint memory spaces. So this is neither sequential program verification nor concurrent program verification, but of course there are similarities as well. So the similarities are, it's like reasoning over two programs at the same time. So one could say construct a single product program. Let us look at these two programs as one program, running at a time, executing instructions of both at a time. And we could perhaps construct such a single product program by a joint walk over their CFGs. And so therefore, instead of a CFG, which is, our basic object on which a lot of compiler static analysis work happens, here we will have to talk about this joint transition graph, where I'm walking over both the source and the target. And the nodes represent program point pairs, and the edges represent what happens between those program point pairs on the source and on the target, right? So that's what is going to be the basic underlying data structure. And in usual program verification, we talk about invariants, which are talking about that program states at different program points. Here we have to talk about relational invariants, because we have to talk about how are the states of the two programs related, right? So it is perhaps not important to say that variable x of the source program is the square of the variable y of the source program, but it's important to say that the variable x of the source program is the same as the variable x in the target program, and the variable y in the source program is the same as whatever the relation between them is okay, but there is this relational invariance that I'll have to get, right? Okay, so here is a quick example. So on the left hand side is a simple program, and if you can see in the loop, there is the statement x is a times a, which is getting executed every single time the loop runs, and so it's redundantly executing that. That code could have been hoisted above. And here is the CFG of that, right? Using some SSA renaming and all of that, that we've already heard about in the morning. So it's not very important to see how this CFG is constructed from there, but what I'm trying to say is that if I give you a program, I can construct a CFG and then I can reason about this CFG. But now what I have is that there is that program, it's the same CFG, and after code hoisting, that CFG looks like this, and here you can see that there is a temporary thing. I don't know whether the cursor is visible. There is a temporary thing that has been computed here, which is the product of the two A's that was happening inside the loop, right? So that has been hoisted above, and that is being used inside the loop directly, right? So it is not executing the multiplication multiple times, computed the product once, and it's just reusing that result. So this is the CFG after optimization. This is the CFG before optimization. We have to walk over these two CFGs at the same time. It has to be a joint walk. So this is possibly one way in which we could jointly walk. You can, you can think of these as I'm starting for both of the programs and I'm ending for both of the programs. There's nothing much more than that in these two things. But then, here it's saying that, well, I'm doing a check in the source program and I'm doing a check in the target program. And false means if the first one evaluates to false and the second one also evaluates to false. True means first one evaluates to true, second one evaluates to true. So one might say that, well, why don't we have true false and false true branches? Yes, we could also have. But remember, these are two versions of the same program. And remember, in our translation validation problem, we said we are going to give the same input to both of them. So whatever the value of A5D would be for this program, this would also have the same value of A5D. So if the source is saying if A5D is greater than 0, the target cannot say A5D is less than 0. Right? So therefore, the false true and true false branches in this specific example is not there. However, if as a result of the compiler optimization, this was some other condition that was getting paired up here, we can indeed have these 4 branches coming out of this joint comparison over here. Right? In this particular case, just 2 branches suffice. And there are some nodes, that I have marked as green and some I have marked as red. I'll just come to them in the next slide. But I just want you to sort of observe this, that this new object that I have created, which is a joint transition graph, looks very similar to this CFGs. Okay? It's just that each of these things here now has 2 instructions, one from the source, one from the target. And so if we just figured out how to do an analysis, I mean, just like for a CFG, we can do all kinds of analysis. If we just figured out how to do an analysis of this, we would probably be okay. I mean, here you can even see a loop back here. There is a back edge, so there is a loop. But when we are analyzing this, we have to keep in mind that the source and the target program are operating on distinct memory spaces, right? So even if they appear to be doing the same thing, or they're actually updating different memory spaces. Okay. So now, very quickly, what are some of the issues in JTG creation? So the first thing, if you focus on this text to the right, I mean, those are the same CFGs and that's part of the same JTG. So it turns out that there are many JTGs that are possible given any 2 CFGs, right? I'm walking over both the CFGs, but I could stop on one and walk a little bit on the other, or stop on that, walk a little bit on that. All of these will give rise to joint transition graphs. So there are many JTGs possible, so we have to construct them wisely. And some of the things that are kind of, folklore in this community is that if this joint walk encounters the same nodes in the source and the target, just like we had over here, right? This was doing this comparison, this was also doing this comparison. There is no need to stop this and go ahead on this, or stop this and go ahead on this. If they're basically executing the same statement, let's execute both of them together. And when we do that, we put that in a green box, saying that they were basically doing the same thing. Okay? So if joint walk encounters the corresponding nodes, we step over both together and mark it as a green node in the JTG. Otherwise, I mean, for example, maybe there is something over here, as you can see, which does not exist over here, right? So now I can't do a joint, I can't step over both of them together at the same time. So then we decide which one are we going to step over, the other one will wait for a while, and then in the other case, we'll step over the other and wait for a while, right? Yes. So, those we have denoted as red nodes. Okay. Now, the point is that really, if this entire JTG was all green nodes, that would be the best possible situation, right? It's saying everything is happening in lockstep, and in fact, if this entire JTG is green nodes, I need to do nothing further. The translation is correct. In fact, there has been no translation at all, right? Because everything is matching up. So if everything is matching up, why should I spend any time trying to check that they're correct? Of course they are correct. So the more the green nodes in this JTG, we are doing better. And of course, if this JTG also becomes small, then it is better. So small JTGs, mostly green, are good. And so the question is, how do we come up with such good JTGs, or quote unquote best JTGs? The bad news, or if you like SAT SMT solvers, maybe the good news is that this is an NP-hard problem, finding the best JTG even for very simple best criteria. but it is in this functional NP class, which means we can actually solve it using SAT solvers. And since SAT solvers are very, very good these days, this actually provides some silver lining that yes, this is a hard problem, but maybe I can solve it in practice. So the static approach is the approach that we take for finding out the best JTG. So what we do is, I mean, once we realize that it can be solved using a SAT solver, we just formulate this entire problem of finding the best JTG as a constrained optimization problem. So essentially, we construct the entire product graph, all possible ways of pairing up statements in the source and target. And we say that, well, we'll only select some nodes and edges according to some constraints. So in the interest of time, let me not go over the constraints, but they're not very hard to see, right? I mean, we basically want something meaningful to come out. So the start node should be there, end node should be there. Everything that I'm selecting should be reachable from the starts node. If I'm selecting a green pair, then I'm moving on both the source and the target. If I'm selecting a red pair, I have to choose. I can either move on the source or on the target, but not both. And then we can formulate an objective function to maximize, which could be the count of green nodes or the number of unselected nodes. If I maximize the number of unselected nodes, I'm minimizing the number of nodes in my JTG, and other criteria are possible. And it turns out that this can be formulated, this whole thing, as a max-SAT problem or as a SAT with binary search. And actually, that's what we do in our approach to come up with optimal JTGs, okay, based on whatever criterion we have given. There's also another approach that is used in the literature, which is called the dynamic approach, where it's like a walk over the joint graph constructed on the fly. So you start from the start pair, and on the fly you determine invariants and also what are the best outgoing edges to take. And here, once again, locally constraint solvers can be used. And this is actually implemented in, for example, the translation validator that Saurav Bansal has been working on, and he has productized it from IIT Delhi, and also in several other things. So there's two ways of constructing a good JTG or a best JTG according to your criterion, okay? So now once the JTG is constructed, I'll just take a few minutes to show what we want to do with this JTG to solve the translation validation problem. So here is, code hoisting again, but I've taken a simpler example. So this X is A star A has been hoisted up. You can clearly see that. And this is one JTG I have constructed over here, where there are 4 green nodes and 2 red nodes. As I said, there could be multiple JTGs that can be constructed, and this JTG looks a bit better because there are 5 green nodes and 1 red node, and most of the things here are green. So maybe we can try to see what we can do with this JTG, right? And I mean, both are correct. Even if you work with this, this is correct. And even if you work with this, this is correct. Both represent joint walks over the CFGs. But then we would like to choose one which is smaller and more green. All right. So let us say I have chosen by whatever means this JTG, right? Maybe I was not smart enough. I chose this. And now what do I do? My goal is to finally say that if I start off with the same inputs for both the source and the target, I'll have the same observable behavior. Here the observable behavior is what is being returned, and the inputs, the values of I and A are what are the inputs that are coming in, right? So basically what I could do now is I have to analyze this JTG, and the way we do it is we now pose it as a data flow problem on this JTG, where our data flow items are equalities between things on the source side and things on the target side. So our data flow items are equalities between corresponding things on the source and target. So to start off with, we say everything was the same because I was going to run them on the same input. And then we, this is just saying that, okay, I just did a comparison, so everything is still the same. And then, of course, this thing changed over here. And we could, in the interest of time, we'll just step over this. And at the end, finally, when I come out over here, I see that X is A star A, small x is A star A, capital X is capital A star capital A, small x is on the source side, capitals are on the target side. But because small a was equal to capital A, therefore small x becomes equal to capital X, and I wasn't changed at all. So the I plus X that is returned here is the same as the I plus X that is returned here. So the observable behavior is the same, right? So we constructed the JTG, did a simple data flow analysis where our, the data flow items are basically equalities between corresponding elements. But in reality, things are not always so nice. I mean, we need to keep track of things which are not just equalities between variables, but maybe one variable on the other side is equal to some expression on the other side. So all of those need to be kept track of. Now, I want to end with this one, which actually shows a very interesting case where it is the same code that I had, but let us say hypothetically my compiler actually made a mistake, and instead of saying star I is 0 over here, it said star I is equal to 1 over here, right? The rest of the thing was all correct and the same. So the mistake happened in the first step, okay? And it did code hoisting, and it gave me this CFG. So now what happens is that I can construct, by a similar means, because of course now these two are not going to match up, so they'll be red nodes. So I can construct a similar JTG over here, and I could start doing my same equality propagation. But now when I say I is equal to I, right? Remember, these are two pointers, okay? So what happens when I say star I is 0, it says, well, since I was equal to I, if I did a normal, data flow kind of analysis for our simple sequential program, it will immediately say star I is also 0 and star capital I is also 0, right? But I have to now keep track of that star capital I is referring to a different memory space and star small I is referring to a different memory space. Otherwise, this is going to cause problem. In fact, that's what I wanted to show, that if you do this whole thing, you will actually get finally I is I and X is X. On both the incoming branches here, I is I and X is X. If I did the analysis, assuming that these were just all operating on the same memory space, okay, on the same address space. So while it looks like a normal CFG problem, like a normal data flow problem, but it is not. We have to be very, very careful, particularly when we are dereferencing addresses. On the stacks, I have to remember that these are two different stacks and so on. Okay. So since Krishna has only left 2 minutes for me, so let me go to the last slide and say that I hope I was able to at least convey to you what the translation validation problem is and why is it important. I certainly have not been able to convey to you all that is needed to solve the problem, but at least some basics of that we need to construct this joint graph and do some analysis of this joint graph, and it cannot be the same as normal sequential program analysis or concurrent program analysis. It has its own features in it. Some more advanced issues are, for example, when we say that something is validated, right? So for example, remember, not in that incorrect translation, but in this case, when we finally said that, okay, I'm figuring out from my data flow analysis that yes, I plus X and I plus X are the same on source and target, I need to be able to give a certificate to the user, right? Because remember, we are worried about compilers doing bad things in the most unsuspecting of times. So if the translation validator says that yes, this compiler is translating this program correctly, I should be able to give a certificate which can be independently and efficiently checked. I mean, if checking the certificate is as good as doing translation validation all over again, then that's not useful. So I should be able to give a certificate that can be efficiently checked and that can be independently checked. It should not depend on how I have done the translation validation, right? I should be able to give you a certificate and you should be able to check it that yes. So for example, one particular kind of certificates could be the joint transition graph itself along with the invariants that we have found. And we can check whether those invariants hold. But there are other ways of giving these certificates. When you talk about more advanced data types, you also have to worry about their memory layout, and is this memory layout itself being changed by the translation process. Often we need to worry about things like on the source and the target program, the heaps are the same except for something. And in that something, some action was going on maybe within a loop. So we have to keep track of these things. And there could be other criteria for goodness of translation. It need not just be observationally, they should be equivalent. For example, is it leaking side channel information? A very interesting case of this is, I might have a piece of code in which there are two branches of an if, and on one branch there are maybe 5 genuine operations, and on the other branch maybe there is just one genuine operation, and you had padded it up with 4 knobs so that one cannot figure out from the execution time which branch you're taking, right? This is actually very commonly used to prevent side channel leakage. But now if the compiler goes and says, oh, 4 knobs on that branch, what are they doing? Let me just get rid of them. You'll suddenly start leaking information, right? So we can try to validate translation for information leakage. Has it affected the power? Somebody in the audience today talked about power. Has it affected the power profile? Has it affected the way the cache is being used? So we can do translation validation with respect to all of these. And I think I've already shown that there are close connections with program verification, specific form of program verification called relational verification, where we are comparing 2 runs of a program, regression verification. So these are also topics that have been studied in the literature and have close connections with translation validation. So I'll stop there, and if there are questions, I'd be happy to take.
Yes, Supratik, very nice talk. Are there specific optimizations which are harder than the ones, I think you listed a few, but I was thinking of something like which we do in C++, like function devirtualization, where we don't know which function it can call, but we can analyze the statically and sometimes can figure out that, okay, it can only call one of these functions or 2 possible functions, and will actually replace it while doing the optimization with them. So are these harder or are there challenges for this?
Yeah, I mean, those are very hard actually to say that for the given program at every place where it has devirtualized it, there could not have been. So the point is it is doable, but it is much harder than the other kind of like code hoisting, constant propagation. And honestly speaking, I mean, we were looking at GCC, so there are some, I think, close to 100 passes, some 90 passes at O3, and a lot of them actually don't do anything for a given program. So there are probably around like 15, 20 of them in any run that are really doing something non-trivial. I mean, we actually haven't even looked at the object-oriented G++, but even some of these actually get very complicated because they're changing some memory maps and this and that. Aggressive optimization, they're doing vectorization, and I mean, yes, there are lots of problems there. This is far from a solved problem. Far from a solved problem.
Hi.
Yeah.
Thanks for the talk. So certain optimizations could change the intermediate results, though the final results could be same. So when you were doing that comparisons at each and every node in the joint transition graph, some of those nodes might not be, the equalities might not be identical, but later in the part, like at the exit of the probably the transition graph, they might be.
Yeah. So I just showed equalities as the bare minimum things that we must track, but equalities actually do not suffice for a lot of optimizations. So as I said, we sometimes keep track of how is a variable in one program related to an expression in the other program. Or is there an inequality between a variable in one program and a variable in the other program?
So let's say like we have a strength reduction where a multiplication operation gets translated to an addition, probably
Yes.
a couple of addition operations.
Yes.
Then the expressions are also different. Then what would you do in that case?
Yeah, so what we do is, so those green blocks are the good blocks. If we get same things at their entry, we get the same things. So for the red blocks, we actually take a stretch of red block,
okay.
and we do a complete program verification over there.
So you do it over the region instead of just one block?
Yes.
All
yes.
right, okay.
Yeah, over the entire region. But making sure that the memories are different. I can't treat it like a normal program.
Right, yes. Right. Okay, thank you.